Okay, so let's say that we have a function y equals a cosine of k x minus vt plus some number delta. So pick some value of time. It could be t equals 0. This looks like cosine kx plus delta. So that's a cosine function that represents the wave at t equals 0. If x equals 0, then we just have cosine of delta. Kx, right? So if kx changes by 2 pi, then we have that the function comes back to itself. So for values such, if we have, for x equal to 2 pi over k, we have that, so the function, that doesn't have to be a peak, but let's just draw the function like that. So if it's the peak, if delta were 0, then that would be the peak. This, right, so this whole thing represents this function at some moment in time. In space, this is the wavelength. And that's what this quantity is. Right, so we come back, it'll come back to this point. It could be, any points from here and then to here. It's the same thing. Come back to that if delta is not equal to 0. So we can say that the wavelength, lambda, is 2 pi over k. But now let's consider this thing moving in time, and a full cycle in time. Then we are referring to kVt, or the special t such that the function repeats itself. So this is 2 pi. Then that means that's the period for an oscillation, and that is therefore 2 pi over kV. So we have the wavelength, we have the period of oscillation. Here we have the x minus vt. So if at t equals 0, and we consider x equals 0, we have some value. But we can get the exact same value at some non-zero t and some non-zero x, such that x minus vt equals 0. So in other words, x equals vt, which is the same thing as saying x minus vt equals 0. This represents the position of the wave, if you will, at x equals 0, and now at a different time it's moving. So at x equals 0 you have some value, and that whatever that value is, that displacement, that's moving. It happens to be moving to the right, and we'll see that. It's moving to the right, and it's at some location at time t. So this represents the speed of the wave, because we can simply do dx by dt, and we get v. So we know that that is the speed of the wave. Right, the constant in front of the t represents the speed of this wave. The frequency is 1 over the period, and so we know that that must be kV over 2 pi, and we know therefore that that's v over lambda. And so we can conclude that the speed of the wave is the wavelength times the frequency. these are all features that we get by analyzing this function.